There's a jet flying right now somewhere over a battlefield that has been called ugly, outdated, obsolete, and destined for retirement for the last 30 years. Politicians have tried to kill it. Bureaucrats have tried to replace it. Defense analysts have written its obituary more times than anyone can count. And every single time the soldiers on the ground, the ones taking fire, the ones pinned down in the dirt with nowhere to go, they keep asking for the same aircraft by name. That aircraft is the A-10 Thunderbolt II. And what is happening to it right now, the upgrades, the modernization, the quiet revolution taking place inside hangars and test facilities across the United States is going to change close air support forever. This is not a story about nostalgia. This is not a story about keeping an old airplane alive because people have feelings about it. This is a story about a machine that was purpose-built to do one specific thing better than anything else ever designed. And what happens when you take that machine and bring it screaming into the 21st century with technology its original designers could never have imagined. Before we go any further, take a second to subscribe if you have not already. Over 98% of viewers watch without subscribing, and it costs you absolutely nothing. Hit that button now so you never miss a story like this one. Let us start at the beginning, because to understand why the new A-10 matters so much, you have to understand what the original A-10 was built to do and why nothing else has ever come close to doing it as well. The year is 1972. The Cold War is at its most dangerous. NATO planners are running war games and the results keep coming back with the same terrifying conclusion. If the Soviet Union rolls its armored divisions through the Fulda Gap in West Germany, if those thousands of tanks and armored vehicles flood across the border, the alliance does not have enough ground forces to stop them. The math is brutal. Soviet armor outnumbers NATO armor by enormous margins in certain scenarios. The only solution, the only realistic counter is air power, but here is the problem. The air power that exists at that moment is not designed for what the military needs. The jets of the early 1970s are fast. They are built for air-to-air combat, for intercepting enemy aircraft, for delivering nuclear weapons at high altitude. They are not built to fly low and slow over a chaotic battlefield, to hunt individual tanks one by one, to absorb gunfire and keep flying, to stay over the fight long enough to actually change the outcome on the ground. So the Air Force runs a competition. They want a new kind of aircraft, not a fighter, not a bomber, something entirely different. A dedicated ground attack aircraft built from the ground up for one mission, destroying enemy armor at low altitude and high-threat environments while keeping its pilot alive long enough to finish the job. Two companies compete. Northrop submits the YA-9. Fairchild Republic submits the YA-10. The Air Force flies both. They test both extensively. And in 1973 they choose the A-10, the aircraft that will become the A-10 Thunderbolt II. But most people, even aviation enthusiasts, do not fully appreciate just how radical the design decisions in that aircraft were. Because every single system, every single feature, every single choice was made with one overriding priority: survive, keep killing tanks, bring the pilot home. The gun comes first. Always, when people talk about the A-10, the conversation almost always starts with the GAU-8 Avenger. And rightly so, because this is not a gun that was mounted on an airplane. This is an airplane that was built around a gun. The GAU-8 Avenger is a 7-barrel rotary autocannon. It fires 30mm depleted uranium rounds. It weighs over 4,000 pounds fully loaded. It is roughly the size of a Volkswagen Beetle. The entire forward section of the aircraft was designed specifically to accommodate this weapon. The nose gear sits slightly off-center so the barrel of the gun can sit on the aircraft's centerline. The titanium tub that protects the pilot, the survival cell, was designed around the dimensions of the gun and its ammunition drum. When the GAU-8 fires, it produces a recoil force of roughly 10,000 pounds. For comparison, the thrust of each of the A-10's two engines is approximately 9,000 pounds. That means when the pilot pulls the trigger, the gun is pushing backward with more force than one of the engines is pushing forward. The aircraft actually slows down slightly when the gun fires. The sound is not a bang. It is not a burst. It is a sound that ground troops have described as the most comforting noise they have ever heard in combat. A deep, grinding mechanical roar. The famous BRRRT that has become a kind of cultural shorthand for close air support itself. At its maximum rate of fire, the gun delivers approximately 65 rounds per second, each round traveling at over 3,000 feet per second, each round capable of penetrating the top armor of virtually any main battle tank built during the Cold War era. In Afghanistan and Iraq and Syria, that gun has been used at lower rates of fire against personnel, light vehicles, and fortified positions. It has stopped ambushes. It has broken through encirclements. It has saved the lives of soldiers and Marines who had no other option left. But the gun is only the beginning of what makes the A-10 what it is. The airframe itself is an engineering philosophy as much as it is a machine. The designers at Fairchild Republic made choices that no fighter aircraft manufacturer would ever make because they were not building a fighter, they were building a flying tank. The cockpit is surrounded by a titanium bathtub. The walls of that bathtub are between half an inch and 1.5 inches thick depending on the location. The titanium is not aluminum, it is not composite, it is titanium. Heavy, expensive, and essentially impervious to small arms fire, and the kind of ground fire the aircraft would face in a low-altitude attack environment. The aircraft has two engines, but they are not placed in the conventional location inside the fuselage. They are mounted in separate pods on either side of the tail. This means that an engine fire in one engine does not automatically spread to the other. It means that shrapnel from one engine explosion cannot take out the second engine. It means the aircraft can fly has flown on one engine in combat. The hydraulic flight control systems have manual backups. The manual backups are a system of cables and pulleys that allow the pilot to fly the aircraft even if every hydraulic system is destroyed. The A-10 has come back from combat with one engine missing large sections of one wing with control surfaces shredded, with holes in the fuselage you could put your head through. It has come back. That is not an accident. That is not luck. That is the direct result of design decisions made 50 years ago by engineers who understood that the aircraft's survivability was not separate from its mission capability. It was the mission capability. A dead pilot kills no tanks. An aircraft that cannot absorb punishment and keep flying cannot provide close air support when close air support matters most, which is when the fighting is the most intense and the threats are the most dangerous. And then there is the speed, or more precisely, the lack of it. The A-10 is slow by jet aircraft standards. Its top speed is around 420 miles per hour. An F-16 can hit 1,500 miles per hour. An F-35 is comparable. Even older jets like the F-4 Phantom were nearly twice as fast as the A-10. For decades, fast jets advocates used this as a primary argument against the A-10. Why keep a slow airplane when you have fast ones? But that argument fundamentally misunderstands what close air support actually requires. A soldier on the ground in contact with the enemy does not need an aircraft flying over at 1,500 miles per hour. At that speed, the pilot has approximately 2 to 3 seconds to identify the target, confirm it is not friendly, aim, fire, and assess. In a close fight where friendly forces and enemy forces may be separated by 100 meters or less, those 2 to 3 seconds are not enough. The A-10 can loiter, it can circle, it can come in at 300 miles per hour, slow enough to really look at what is happening on the ground, slow enough for a pilot to build a mental picture of the fight, identify the enemy position, confirm the friendly position, and put ordnance exactly where it needs to go. That loiter time is not a weakness. In close air support, it is the single most important performance characteristic after survivability. The soldiers on the ground are not calling for air support during a brief moment of contact. They are calling because they are in sustained contact. They need an aircraft that can stay with them, not one that roars through at supersonic speed and is gone before the smoke clears. Now here is where the story gets to what is happening right now today and why it changes everything. For years, the A-10 has been flying essentially the same technology it flew with in the 1990s. The aircraft was updated in the 1990s to the A-10C standard, which brought significant improvements including digital cockpit displays, GPS-guided weapons compatibility, and the ability to carry the Lightning and Sniper targeting pods. Those upgrades were genuinely significant. But compared to the sensor technology, the communication systems, the weapons available today, the A-10C of a decade ago was still operating with equipment a full generation behind the most advanced tactical aircraft in the inventory. The Air Force kept trying to retire the aircraft. The Army kept opposing the retirement. Ground commanders kept writing letters and testimony. Pilots who flew the mission kept making the case. And through all of it, the A-10 kept flying. And while the retirement debate raged, something else was happening quietly. Engineers were working. Contractors were developing. The Air Force was investing in upgrades that would take the A-10 and bring it into a completely different era of capability. What has emerged is not a replacement for the A-10, it is the A-10 transformed. Let us talk about what is actually changing and why each piece of it matters. Start with the wings. The original A-10 wings were designed and built in the 1970s. They are extraordinarily strong, purpose-built for low-altitude, high-stress maneuvering, for pulling out of dive attacks over targets, for sustaining the kind of G-forces that close air support profiles generate. But they are old. Metal fatigue is real. The Air Force tracked the remaining service life of its A-10 fleet and found that many aircraft were approaching the limits of their structural airframe hours on the original wings. So the service launched the A-10 wing replacement program. And this is not a repair program. This is not patchwork. The Air Force is replacing the wings on A-10s with entirely new manufactured wings that restore full structural service life to the airframe. Each set of replacement wings gives an aircraft roughly 10,000 additional airframe hours. That is decades of additional service life. That decision alone tells you everything you need to know about the institutional commitment to this aircraft. When an Air Force installs brand new wings on an airplane, that Air Force is not planning to retire that airplane anytime soon. The wing replacement program ensures that the A-10 airframes that receive them will still be flying into the 2030s and potentially beyond, long enough for all of the other upgrades being developed and fielded right now to fully mature and demonstrate their impact. Now let us talk about the sensors and targeting systems, because this is where the new A-10 genuinely becomes something its designers never envisioned. The current generation A-10C carries the Sniper Advanced Targeting Pod. This is a remarkable piece of equipment. It provides long-range targeting and identification capability, laser designation for precision-guided munitions, infrared and electro-optical sensors that allow the pilot to see targets clearly in daylight and darkness, and a data link that allows imagery to be shared with ground forces and other aircraft. But the upgrades currently being integrated and tested go well beyond the Sniper Pod. The Air Force is working on integration of advanced electro-optical infrared systems that provide significantly greater resolution and range than legacy pods, sensors that can detect and classify targets at standoff ranges that allow the aircraft to stay outside the engagement envelope of modern man-portable air defense systems while still identifying and engaging targets with precision. Consider what this means in practice. One of the primary arguments for retiring the A-10 was that the threat environment had changed. When the aircraft was designed, the anti-aircraft threat was primarily radar-guided systems and conventional anti-aircraft artillery. Modern battlefields are saturated with man-portable surface-to-air missiles, sophisticated shoulder-fired weapons that can engage low-flying aircraft at ranges and altitudes that were previously considered safe. The response to this threat was, for years, assumed to be speed and altitude. Go higher, go faster, and the shoulder-fired missiles cannot reach you. But if you go high and fast, you lose the ability to do close air support. You lose the identification capability. You lose the loiter time. You lose the direct relationship between the aircraft and the soldier on the ground that has made close air support decisive in every conflict since Vietnam. The new sensor suite changes this equation. With sensors capable of identifying and precisely engaging targets from significantly greater standoff distances while still maintaining the ability to close in when necessary, the A-10 can operate in a way that manages the MANPADS threat more effectively than simply going faster and higher. It keeps the aircraft in the fight in a way that a high-altitude fast jet simply cannot replicate. The communication systems being integrated into the modernized A-10 fleet represent another quantum leap in capability. This matters more than most people outside the military community realize. Close air support is fundamentally a communications challenge as much as it is a firepower challenge. The pilot needs to hear and understand the ground controller. The ground controller needs to be able to describe the target, the friendly positions, the restrictions, the threats, all in real time, all under extreme stress, often while taking fire. The aircraft needs to be able to pass information to other aircraft, to command and control nodes, to intelligence assets. In older configurations, a significant percentage of communication breakdowns in close air support occurred not because of pilot error or controller error, but because the communications system simply could not handle the density of traffic and the quality of transmission required. The new A-10 modernization program includes integration of wideband satellite communications systems that provide high-bandwidth voice and data connectivity even when the aircraft is in terrain-masked environments, low in mountain valleys below ridgelines. It includes updated Link 16 data link capability that allows the aircraft to share and receive tactical pictures in real time, to see where friendly aircraft are operating, to receive updated target information, to pass imagery and coordinates without a voice transmission at all. It includes integration with the rover system that allows ground controllers and the aircraft to share live sensor video, so the person on the ground can see exactly what the pilot is looking at, so there is no ambiguity about which building, which vehicle, which individual they are talking about. When a ground controller and a pilot can share a live feed of the same image, the probability of a targeting error drops dramatically. The probability of getting the right weapon on the right target at the right time increases in ways that are difficult to overstate. Then there is the weapons integration story, and this is where the new becomes genuinely revolutionary. The original A-10 was designed to carry iron bombs, Maverick missiles, and the GAU-8. The A-10C upgrade in the 1990s added GPS-guided weapons, joint direct attack munitions, and small-diameter bombs. But the weapons being integrated onto the modernized aircraft go well beyond those capabilities. The A-10 is being qualified to carry the AGM-65 Maverick in its most modern variants, updated versions with improved seekers that can engage targets the original Maverick would have struggled to reliably acquire. The aircraft is being integrated with the GBU-39 small diameter bomb, which allows a single A-10 to carry far more individual precision-guided weapons per sortie than was previously possible. Where an older A-10 might have delivered 2 or 4 precision-guided weapons per sortie, an aircraft carrying multiple small-diameter bombs can engage 8, 12, or more individual targets in a single flight. In a close air support scenario where there are multiple enemy positions, multiple vehicle targets, multiple crew-served weapons, that multiplication of per sortie effectiveness is tactically decisive. The aircraft is also being evaluated for the Advanced Precision Kill Weapon System, the laser-guided rocket that uses a laser seeker on a standard 2.75-inch rocket to provide pinpoint accuracy. This weapon is transformative for close air support because it gives the aircraft a precision standoff capability in the rocket category. A weapon type that carries a much smaller warhead than a 500-pound bomb, but is more than adequate for many close air support targets, with a cost per round that is a tiny fraction of a precision-guided bomb. In situations where ground forces need a building cleared or a crew-served weapon destroyed, a precision rocket is often more appropriate than a 500-pound bomb. The blast radius of a large guided bomb in a close fight creates its own risks. Precision rockets allow the aircraft to apply exactly the right level of force to the exact right point. And then there is the integration of the collaborative combat aircraft concept, unmanned wingmen, into the A-10's operational future, and this is the piece of the story that most people have not yet heard. The Air Force is developing what it calls the Collaborative Combat Aircraft Program, autonomous or semi-autonomous unmanned aircraft that can operate alongside manned tactical aircraft, extending their sensor reach, carrying additional weapons, providing threat detection and jamming capability. The initial development of this program is focused on fifth-generation fighters, the F-35 and the Next-Generation Air Dominance program. But the mission sets where this capability would be most transformative include close air support, and the A-10 is uniquely suited to serve as a controlling node for collaborative unmanned aircraft in that mission set. Here's the concept in practice. An A-10 pilot arrives over a complex close fight. There are enemy armored vehicles, there are fortified positions, there are high-value individuals moving through an urban environment, and there are civilian areas that must not be struck. In the legacy configuration, the A-10 pilot has their own sensors, their own weapons, and the information coming from the ground controller. In the collaborative concept, the A-10 pilot controls one or more unmanned aircraft that are providing additional sensor coverage of the battlefield, painting targets for the A-10's weapons, carrying additional precision-guided munitions that the manned aircraft can deploy without needing to reposition, and providing electronic warfare coverage that degrades the enemy's ability to engage the A-10 with air defense systems. The manned aircraft, the pilot, retains decision authority. The unmanned aircraft extend the reach, the persistence, and the lethality of the overall system without removing the human judgment that close air support demands. This is not theoretical. The Air Force has been demonstrating the core technologies for years across multiple programs. The integration of those technologies with a modernized A-10 as the controlling platform for close air support in complex environments represents a capability leap that would make the new A-10 more effective per sortie than anything that has ever flown that mission before. Let us talk about the people who fly this mission, because the aircraft is only part of the story. The human dimension of close air support is something that no amount of technology can fully replace, and that the A-10 community has preserved and developed in ways that are unique in tactical aviation. The A-10 pilot community is distinct. It is different from the fighter community in ways that go beyond the aircraft they fly. Fighter pilots are trained to think fast, to make split-second decisions, to engage and disengage, to operate in the third dimension, altitude and speed, as their primary tactical parameters. A-10 pilots are trained to think about the ground. They are trained to read a close fight, to understand infantry tactics, to know where friendly forces are most likely to be, to understand the difference between an attack by fire position and an assault position, to communicate with ground controllers in the specific language of Joint Terminal Attack Control. Many A-10 pilots have spent significant time with ground combat units learning the fight from the soldier's perspective. The community has a culture of direct partnership with the infantry and armor community that is genuinely uncommon in aviation. When a soldier calls for close air support and hears an A-10 pilot's voice on the radio, there is a shared language, a shared tactical vocabulary, a shared understanding of what the ground controller needs and what the aircraft can provide. That relationship is not incidental. It is not just a cultural preference. It produces measurably better close air support outcomes. Communication clarity goes up. Misidentification events go down. The aircraft's capability is employed in the way that most effectively supports what is happening on the ground rather than being applied in ways that look correct from altitude but miss the tactical reality at the soldier's level. The modernization effort is investing in this human dimension as well. Updated mission systems trainers that replicate the full capability of the new sensor and communications suite allow pilots to build proficiency with the new systems before they ever fly with them in a real close support scenario. The new trainer configurations include high-fidelity simulation of the ground controller interface, so pilots can practice the exact communication protocols that the new systems enable with a simulated ground force in contact, building the mental and procedural muscle memory that makes those systems effective under the stress of a real fight. The Air Force is also investing in expanded joint training between A-10 units and ground combat units, exercises where pilots spend time embedded with infantry, where JTACs spend time flying in the backseat of training aircraft with A-10 pilots, where both communities develop the shared understanding that produces the best close air support outcomes. This investment in joint training is not happening because the Air Force suddenly decided it was important. It is happening because decades of actual combat have produced clear, documented evidence that the quality of the pilot-to-controller relationship is a primary driver of close air support effectiveness, and that relationship requires deliberate, sustained investment to maintain. Now let us address the argument that has been used to try to retire the A-10 for 3 decades, because that argument is not going to disappear just because the modernization program is proceeding. The argument goes like this. The A-10 is a single-role aircraft. It does only one thing: close air support. The F-35 can do close air support plus air-to-air combat plus electronic warfare plus strategic strike plus intelligence gathering plus virtually everything else. In a world of constrained defense budgets, is it not more efficient to buy one aircraft that does everything rather than maintain a specialized aircraft that does only one thing? On the surface, this argument sounds logical, but it contains a fundamental misunderstanding of what close air support actually requires and what happens to military capability when specialized functions are absorbed into general-purpose platforms. The F-35 can do close air support, that is true, but the F-35's close air support capability involves flying a laser-designated or GPS-guided weapon from relatively high altitude, typically above 15,000 feet, to avoid the threat environment that exists closer to the ground. That works against static targets, against targets that have been pre-identified and pre-designated. Against the kind of dynamic close fight where soldiers are in direct contact with an enemy that is moving, changing positions, using cover, blending with civilian surroundings, the F-35's high-altitude fast-pass approach has real limitations. The pilot has seconds over the target. The sensor picture from 15,000 feet in an electro-optical pod, while excellent, is fundamentally different from the picture a pilot has when they are down at 2,000 feet, circling the fight, watching it develop, building the situational awareness that allows them to engage the right target with the right weapon at the right moment. The F-35 also costs approximately $100 million per aircraft. The fully modernized A-10 with all of the upgrades described in this program costs a tiny fraction of that per airframe. The cost per flight hour of the A-10 is significantly lower than the F-35. In a budget environment where every dollar spent on defense has to be justified, the cost efficiency of a highly capable specialized close air support aircraft operating alongside multi-role fighters that handle the missions requiring high performance is a legitimate operational and financial argument. Specialization exists in military forces for exactly this reason. Not every soldier in an army is a special operator. Not every ship in a navy is a carrier. Not every aircraft in an air force needs to be a multi-role fifth-generation fighter. Specialization, done correctly, with the right equipment for the right mission, produces better outcomes than generalization. There's also the argument from the threat environment. Critics of the A-10 argue that the aircraft cannot survive in a high-end threat environment, that modern integrated air defense systems would destroy it before it could reach its targets, that the low-altitude slow-speed profile that makes it effective in close support is a death sentence in a near-peer conflict. This argument is more serious than the efficiency argument, and it deserves a serious answer. And the answer comes from the modernization program itself. The A-10 was never designed to operate in the teeth of a fully integrated modern air defense system without support. No aircraft is. The joint force approach to high-end conflict involves suppression of enemy air defenses SEAD missions, jamming aircraft, cyber operations against radar and missile systems, and the use of stealth aircraft and standoff weapons to degrade the air defense network before other aircraft enter the contested space. The A-10's role in high-end conflict is not to fly through the most dangerous defended airspace. It is to be the most effective close support aircraft available once that airspace has been sufficiently opened. The new sensor systems that allow engagement from greater standoff distances directly address the MANPADS threat that has been the most realistic air defense concern in recent conflicts. The new electronic warfare compatibility being developed for the aircraft addresses the radar-guided threat. The aircraft is becoming more survivable in exactly the threat environments where it operates, while maintaining the low-cost, long-loiter, heavy firepower characteristics that make it irreplaceable for the close support mission. Consider the broader context of where the United States military is operating and where it is likely to operate in the future. Post-9/11 era produced 20 years of counterinsurgency, 20 years of close air support in environments where the air threat was minimal, but the ground threat was constant and complex. The A-10 was the most used, most requested close air support aircraft in that entire era. But military planners are now focused on near-peer competition. They are looking at scenarios involving Russia or China or both. And in those scenarios, the demand for close air support does not disappear. It actually increases. Near-peer ground forces are equipped with massive amounts of armor, with artillery, with rocket systems, with anti-tank guided missiles, with all of the heavy weapons that the A-10 was originally designed to defeat in 1972. The scenarios that kept NATO planners awake in the Cold War are back. And the aircraft that was built to answer those scenarios, upgraded with the sensors and weapons and communications of the 21st century, is more relevant to those scenarios than it has ever been. The A-10 was designed to kill Soviet armor at the Fulda Gap. The threats it would face in a near-peer conflict have changed. The armor it would need to destroy has updated its own systems and protection. But the fundamental challenge of destroying large numbers of armored vehicles at low altitude in a high-threat environment remains exactly what it was when Fairchild Republic won that contract in 1973. And the A-10, modernized, remains the most capable aircraft ever built for exactly that challenge. Let us talk about some specific upgrades that have not received as much public attention, but that represent genuinely significant improvements to the aircraft's combat effectiveness. The helmet-mounted cueing system integration is one of these. The legacy A-10 cockpit required the pilot to align the aircraft with a target before engaging it with most weapons. The pilot aimed the aircraft and the aircraft aimed the weapon. Modern helmet-mounted cueing systems change this relationship fundamentally. The pilot looks at a target, and the system cues the weapon to the direction the pilot is looking. This seems simple, but the tactical implications are profound. A pilot in a turning engagement over a close fight can engage a target on one side of the aircraft's flight path without having to maneuver directly toward it, reducing the time the aircraft is exposed to ground fire during an attack run. In urban environments where targets can appear and disappear quickly, the helmet cueing system allows faster, more responsive engagement of fleeting targets. In any engagement where speed of weapons employment matters, which is most engagements, the helmet cueing system represents a meaningful improvement in the pilot's ability to put the first round on target before the target can react or relocate. The cockpit modernization program more broadly is addressing one of the few genuine criticisms that A-10 pilots themselves have made about the aircraft. The original cockpit, even in the A-10C configuration, uses older display technology and a human-machine interface that is more demanding to operate under stress than modern large-screen glass cockpit systems. The upgrade program is replacing legacy displays with large-format color multifunction, displays that present information more clearly, that integrate sensor and weapons and navigation information in a more intuitive format, and that reduce the cognitive workload on the pilot at precisely the moments when cognitive workload is highest, during an active close air support engagement where the pilot is simultaneously managing the aircraft, communicating with ground controllers, monitoring threats, and preparing to employ weapons. The terrain following and low-altitude navigation system upgrades deserve attention as well. The A-10 has always operated at low altitude, but operating at low altitude at night, in poor weather, in mountainous terrain, in hostile jamming environments, is enormously demanding and has historically required exceptional pilot skill to do safely. The GPS and terrain awareness system upgrades being integrated into the modernized aircraft provide the pilot with a real-time picture of the terrain around the aircraft, alert for terrain conflicts before they become critical, and provide navigation accuracy in GPS-degraded environments through integration of inertial navigation systems and terrain-referenced navigation technology. In a near-peer conflict where GPS jamming is a near certainty, this degraded environment navigation capability is not a nice-to-have. It is essential for the aircraft to operate at low altitude without a prohibitively high risk of controlled flight into terrain. The electronic warfare upgrades are similarly essential. The legacy A-10 carried radar warning receivers and countermeasures dispensers, chaff, and flares to degrade the effectiveness of radar-guided and infrared-guided missiles. The modernized aircraft is being equipped with updated radar warning receivers that provide better detection and classification of modern radar threats, with more advanced countermeasures systems that are more effective against the specific missile seekers found on current and anticipated threat systems, and with integration pathways to towed decoy systems that have proven highly effective against modern radar-guided missiles in both testing and operational use. The towed decoy concept involves the aircraft dispensing a small electronic device on a cable that mimics the aircraft's radar signature at a displaced location, causing radar-guided missiles to guide toward the decoy rather than the aircraft. This technology has been in service on other aircraft for years, and has a documented record of effectiveness against precisely the radar-guided threats that most concern planners thinking about A-10 survivability in a near-peer environment. Let us spend some time on the specific close air support scenarios where the modernized A-10 will demonstrate its most decisive advantages, because the abstract description of upgraded systems only tells part of the story. Imagine a conventional near-peer conflict in Eastern Europe. Ground forces are in contact with a well-equipped adversary that has significant armor, artillery, and anti-tank guided missile capability. Friendly ground forces are advancing on a fortified position but are being engaged by enemy armor from multiple directions. The enemy has 2 tanks and 3 infantry fighting vehicles in a tree line to the north, a battery of self-propelled artillery approximately 8 kilometers to the east, and a crew-served anti-tank guided missile team in a farmhouse to the west. The close air support request comes in. A flight of 2 modernized A-10s arrives over the battle space. The lead pilot connects to the ground controller's rover feed. He can see the controller's view of the battlefield in real time. The controller designates the priority target, the anti-tank guided missile team in the farmhouse. The A-10 lead identifies the structure, confirms the grid with the controller, and delivers a small diameter bomb from a standoff distance that keeps the aircraft above the engagement envelope of the MAMPADS threat in the area. The farmhouse is destroyed with minimal blast radius, no collateral damage to adjacent structures where civilians may be present. The wingman aircraft, using the advanced targeting pod, is simultaneously building a picture of the tank and IFV position in the tree line to the north. The controller confirms the target set. The wingman employs 2 AGM-65 Mavericks in rapid succession against the 2 tanks, then rolls in with the GAU-8 for a strafing pass against the infantry fighting vehicles, destroying 2 of the 3 in a single pass. The lead aircraft, having expended its initial weapon, repositions to engage the 3rd IFV with a precision rocket. The entire sequence, from initial radio contact to the destruction of all 6 targets, takes approximately 11 minutes. The artillery battery to the east is relayed to a higher command node and targeted by a long-range strike system. The ground forces resume their advance. This scenario would have been impossible with the A-10 as it existed 10 years ago, not because the pilot was less skilled or less brave, but because the sensors, the weapons, and the communication systems that allow the entire sequence to happen with the speed, precision, and coordination described here simply did not exist in the A-10's inventory. They do now, or they will shortly, as the modernization program reaches full maturity. Now consider the urban close air support scenario, which has been the dominant operational environment since 2003 and which will remain a primary close air support challenge for the foreseeable future. Urban environments are where close air support is simultaneously most needed and most dangerous to employ. The density of civilian infrastructure, the proximity of civilian populations, the complexity of the target environment, the tendency of adversaries to exploit all of it to complicate identification and engagement. All of these factors make the precise application of firepower in urban terrain the hardest problem in tactical aviation. The modernized A-10's sensor suite, communications integration, and precision weapons options are specifically designed to address this challenge in ways that previous versions of the aircraft could not. The combination of high-resolution electro-optical infrared sensors, helmet-mounted cueing, rover integration with ground controllers, and precision munitions that allow selection of exactly the right warhead, Size for the target means that an A-10 pilot over a complex urban fight has more tools for discriminating between legitimate targets and protected objects than any previous close air support aircraft. The precision rocket option is particularly important here. A 2-pound warhead precision rocket against a window, against a specific room in a building, against a vehicle in an alley, produces an effect completely appropriate to the target with an explosion that does not threaten the building next door. That level of surgical application of firepower in an urban fight is new. It represents a genuine capability that did not exist for the A-10 community even 5 years ago. And it is exactly the kind of capability that will define effective close air support in the complex conflicts the 21st century is generating. There is another dimension of the new A-10's revolutionary character that has not yet been fully appreciated outside the specialist community, and that is the aircraft's role in what the military calls multi-domain operations. Multi-domain operations is the concept that modern military operations are fought across land, sea, air, space, and cyberspace simultaneously, and that units across all domains must be able to share information and coordinate action in real time to achieve decisive effects. For close air support, this means an A-10 pilot over a ground fight needs to be connected to satellite systems providing targeting information, to ground units sharing sensor feeds, to other aircraft building a combined picture of the battle space, to intelligence systems processing signals and imagery, and to command and control nodes that can redirect effort based on how the fight is evolving. The legacy A-10, for all its combat effectiveness, was a relatively isolated system. Its communications were adequate for talking to a ground controller, but limited in their ability to participate in the broader information environment that multi-domain operations require. The modernized aircraft with updated data links, satellite communications, improved integration with national intelligence systems, and the ability to serve as a node in the collaborative unmanned aircraft network, is genuinely a multi-domain participant. Information flows to and from the aircraft in ways that make it more effective, and that make the joint force more effective as a result. A sensor cued by a satellite passed through a data link to an A-10's targeting pod designated by the A-10's laser and engaged with a precision-guided munition, all within a targeting cycle measured in minutes rather than hours, represents exactly the kind of kill chain compression that multi-domain operations require. The A-10 in this architecture is not the old slow airplane on the edge of the modern force. It is the delivery node, the thing at the end of the information chain that turns data into destructive effect precisely where the soldier on the ground needs it most. Let us spend a moment on the international dimension of this story because it matters for understanding the broader significance of the A-10 modernization program. The United States has transferred A-10 aircraft to partner nations in the past, and the question of whether modernized A-10s could be offered through foreign military sales programs is relevant to the aircraft's long-term future. Several NATO allies and partner nations operate in environments where close air support is a primary air power requirement, and where the cost of fifth-generation multi-role fighters is beyond their defense budgets. A modernized A-10 offered through foreign military sales would give those nations a genuinely world-class close air support capability at a cost that is achievable. It would also extend the production of spare parts, the development of improved systems, and the overall industrial base that supports the A-10 fleet, potentially reducing per-aircraft costs for the U.S. Air Force as well. Beyond direct aircraft transfers, the development of combined close air support doctrine and training with allied nations that operate in the same mission space is enormously valuable. The ability to integrate close support into allied ground force operations, to train allied forward air controllers to work with A-10 pilots, to develop shared procedures and communications protocols, extends the operational reach of close air support capability across the alliance in ways that a purely American program cannot. NATO's collective defense depends on allied forces being able to operate effectively together, and close air support integration across allied air and ground forces is a genuine operational requirement that the modernized A-10's capabilities directly address. The story of the A-10's survival against repeated retirement attempts and its current modernization renaissance is ultimately a story about the nature of military expertise and the importance of listening to the people who actually do the fighting. Every time the A-10 has faced a serious retirement attempt, the most persuasive arguments for keeping it have come from the ground. From special operations forces who have called for A-10 support in the most desperate circumstances imaginable and who are alive today because the aircraft showed up. From Army and Marine Corps officers who have led troops in contact and who understand viscerally the difference between a fast-moving jet that passes over once and an A-10 that stays in the fight, that talks to the ground controller, that circles and watches and engages with the precision that comes from a pilot who can actually see what is happening. From combat medics and infantry squad leaders and platoon commanders who have written after-action reports describing exactly what the A-10's presence and firepower meant to the outcome of a firefight. The Air Force bureaucracy, budget planners, and systems analysts can model efficiency and cost per flying hour and multi-role capability. They cannot model the confidence that comes to soldiers in contact when they hear that sound overhead. They cannot model the tactical effect of an aircraft that can stay with a ground unit for an extended engagement, learn the fight, and apply precision firepower over and over until the threat is defeated. The modernization program is, in some ways, the institution finally catching up with what the operators have known for years. The A-10 is not a relic. It is not a sentimental favorite. It is the most capable close air support aircraft ever designed, and with the upgrades now being integrated, it